good morning, everyone, and afternoon. I see one or two people in different time zones. I can see Dave here in Mountain Time, so good afternoon, Dave. So I'm Brendan Bradley. For those of you that I haven't met, it's my great pleasure to introduce Dr. Robin Lee for this seminar. But before I do, just briefly mentioning that this is part of the QuakeCoRE monthly seminar series. You can see on the shared slide that this is second Friday of every month at 10 a.m. New Zealand time. And you can see at the bit link below the seminar series that we've had for 2023. And I guess just a broad announcement that if you are interested yourself or you know someone else that you think would be a great speaker, please get in touch with myself, the administration team, or someone in the leadership team to express your interest or to nominate someone else to speak in 2024. So with that, Robin is going to be speaking to us in an area of his research expertise and experience, specifically associated with the role that he's played in the development of the National Seismic Hazard Model for New Zealand. Many of you will be familiar with the National Seismic Hazard Model. It's essentially a 12-year update from the last previous version, and Robin played a significant role in one half of the problem associated with ground motion characterization that he's going to teach us a little bit more about. Just by way of introduction, Robin completed his PhD at the University of Canterbury in 2017. And then after a few years stint as a Rutherford Foundation postdoctoral fellow, he started on the academic staff in civil and natural resources engineering at the University of Canterbury as a lecturer. So Robin, with that brief introduction, over to you, and look forward to hearing your talk. And then of course, we'll have plenty of opportunity for questions at the end for people that have them.
Great, thanks. Thanks, Brendan. So as mentioned, the presentation today is going to be titled A Summary of the Ground Motion Characterization Modelling for the 2022 New Zealand National Seismic Hazard Model. And of course, I'm presenting this, but it was work done by a very large team of people. So it's on behalf of the Ground Motion Characterization Modelling team. Credits to Brendan and Sanjay for actually being the GMCM co-leads, and also a special shout out to Matt Gerstenberger for being the lead of the entire project, and also for giving a very good seminar within the series earlier in the year as well. So hopefully people have kind of seen that one and have a fair idea about what the National Seismic Hazard Model is. I'm going to be talking on kind of one half of it, or one very particular part of it, like Brendan mentioned. Here is the, I guess, research map for QuakeCoRE with all the disciplinary themes and interdisciplinary programs and the different coordination mechanisms. And if I was going to place this within one piece of the QuakeCoRE research map, of course, it makes sense that this is mostly aligned with the disciplinary theme 1 on integrated seismic geohazards. But what you can hopefully appreciate is that because it is related to the National Seismic Hazard Model and QuakeCoRE is the New Zealand Centre for Earthquake Resilience, it really kind of feeds into most things that we do at QuakeCoRE. So one slide overview of National Seismic Hazard Model. So as Brendan mentioned, primarily there are two parts to the problem. The first one is the seismicity rate model, SRM, which is basically a model that hosts all the different alternative rupture models or forecasts that we believe to be plausible. And then the other side is the ground motion characterization model. So I just have a picture of a whole lot of alternative ground motion models that we considered as a part of this work, plotted as peak ground acceleration versus distance for a particular scenario. If we were to combine these two components, of course, that is when we get our seismic hazard results. Here I'm just kind of showing one of the hazard maps that have come out of the model for peak ground deceleration corresponding to 10% probability of exceedance in 50 years. This is essentially like a ground shaking intensity forecast. There are other components of the National Seismic Hazard Model. So I've listed just two up here. Of course, there's the service delivery, which is important as well. We can produce these results, but if we don't know how to retain them, process them, and disseminate them, then they're not worth a whole lot. And then there's also a separate working group that is looking at site response modeling in the Wellington Basin. The part that I'm going to be talking about today is the ground motion characterization model. So the product of this ground motion characterization model is essentially a logic tree and the associated weights as determined through some expert elicitation. But what I want to do today is talk you through a lot of the information and analysis that we did and a lot of the decisions that we made along the way to get to that logic tree. So starting at the very top, the first thing we really did was create a ground motion database, or a new ground motion database. Acronym for that one's going to be GMDB. And of course, we have a site characterization database that feeds into that as well. That was developed by Liam Witherspoon. This ground motion database served two main purposes. The first one is through the development of new ground motion models. So GMMs is the acronym I'm going to be using for ground motion models. And we had two, one developed by Gail Atkinson and then one developed by Peter Stafford, two very well-known people within the ground motion modeling and seismic hazard analysis community. Then the second purpose of this ground motion database is going to be using it to evaluate those new models and also existing ground motion models against our observational records. We have limitations with our ground motion database in the sense that we only have so many large magnitude earthquakes that have been recorded in New Zealand's history. So there are limitations associated with that. So we did also have to make some kind of holistic assessments of the ground motion models and also some first order adjustments. That was not all necessarily in sequence, but more of an iterative process. But eventually, using all that information, we made our decisions, did our expert elicitation, and got our logic tree and weights. The last thing I'll talk about beyond that is actually looking at the results of our ground motion characterization modeling and examining hazard sensitivities. So basically, when we update one thing, what does that actually mean in terms of how the hazard changes or the calculated hazard changes? So we can try and understand what the influence of each change is. So I don't have time to talk through every single piece of this in detail. So for each of these, I'm kind of going to just touch on a few of the kind of key aspects of them, starting with the ground motion database. So what is the ground motion database? Fundamentally, it is a relational database of ground motion intensity measures and then the associated earthquake path and site metadata. So here's just a schematic of the database, not expecting you to read everything, but we can see that there are a few kind of tables that are related between each other. The one that I'm kind of circling here is the earthquake rupture table, which kind of hosts all the information related to the earthquakes. On the left, a site table. So coming from work that Liam did, basically a table that has all the metadata associated with any particular site or station. We have a propagation path table, which tells us kind of the distances between the sites and the earthquakes. And then the last one that's important for this presentation is the ground motion intensity measure table on the right here, which is essentially all the kind of calculated ground motion intensities like peak ground acceleration, peak ground velocity, and spectral acceleration. So the purpose of this really is, as mentioned on the last slide, for the development of new ground motion models and also the evaluation of ground motion models. The last thing that I'll mention on the slide, though, is you don't have to know how to use a relational database of any sort to use this ground motion database. It does also come as a user-friendly flat file that's very easy to use. So if you're interested, I have a link at the end of this presentation that kind of shows you where the ground motion database is currently being hosted on the internet. So just two map plots here on the left showing the earthquakes that are a part of the first version of the ground motion database. So each circle kind of indicating a location or the epicenter of a different earthquake that is in the database. So at this stage in this plot, which is on the version 1 database, a lot of them, we'll mention how we kind of trim this back in a few slides from now. But then on the right-hand side, a map plot showing in the pink triangles, all the different kind of ground motion recording stations that are used or included as a part of that ground motion database as well. Here are a few kind of scatter plots of magnitude versus distance for every ground motion record that is included in the database. And I will mention that this plot I've included is for the most recent version of the database, not the version 1, but one that we've just released, version 3.4. I use this one because it looks nicer. But basically, each point on here is a ground motion recording, and then the magnitude of the earthquake that caused it on the y-axis, and then the distance that site that recorded it is from the earthquake on the x-axis. The green circles are our crustal earthquakes, So we see up all the way up here at a magnitude of about 7.8 is our QuakeCoRE earthquake. Down here, magnitude 7.1 is the Darfield earthquake, and then a whole lot of other kind of major earthquakes down within this range. So there's a good amount of data there, but actually when it comes down to it and thinking about what kind of scenarios to actually dominate the hazard, large magnitude, short source sight distance, actually we are still deficient in the data that we have. Slab earthquakes are the ones shown in blue triangles here. And then the other one that's important would be the interface earthquakes over on the right-hand panel here, which are the pink circles. The thing that I want to mention is on the right-hand side of the slide is the number of data or the quantity of data that we have in this database. So if we think back to Chris Van Hout's 2017 strong motion database, which I guess was the predecessor to this ground motion database, it had about 277 earthquakes in it, 415 recording stations, and that kind of culminated in about 4,300 ground motion records. For our version 1 of the ground motion database, we had this approach where we would be kind of all-inclusive and have everything in there. So we ended up with very large numbers, like almost 11,000 earthquakes, 520 odd stations, and about 190,000 ground motion records. But of course, a lot of those are not necessarily relevant for ground motion modeling applications. They're the earthquakes that are far offshore or low quality in terms of the metadata. So we've actually kind of trimmed back on that sequentially, and we've kind of just arrived at our version 3.4, as I mentioned, where we've got a lot more quality control on things, and about 5,400 earthquakes, about 360 stations, and about 33,000 records. I will mention that in terms of our evaluation that I'm going to show as a part of this presentation, I did use the version 1 database because that's the one that was available at the time when we did the work, but I did apply a whole lot of quality constraint and quality control and ended up with these numbers here, which are a bit smaller than what we're seeing in terms of the full databases. But for any of these three kind of sets of numbers, we can see that it is by and large a very big improvement over the previous Van Hout 2017 strong motion database. So going back to this GMCM overview map, the next thing I'm going to talk about is the new ground motion models. So just one slide to explain it. I wasn't involved in the development of these, but of course, Peter Stafford and Gail Atkinson used the ground motion database to develop two new New Zealand specific ground motion models. They use this backbone modeling framework, which is essentially where they have not just a particular prediction, but actually multiple branches that are able to quantify and account for the epistemic uncertainty associated with the ground motions. So a very good modeling approach, although I have to mention that for any model that is New Zealand specific, they were not actually derived solely from New Zealand data, but they used some kind of global model first to account for appropriate scaling of particular parameters, but then were adjusted to New Zealand conditions using the additional data. And that is the case for these two as well. Next thing is two parts: the evaluation of the new and existing ground motion models against records. And as a part of that, towards the end, also the holistic assessment that we made and a few first order adjustments, although not all of them. So starting again with the what, basically we went through and evaluated the accuracy and precision of ground motion models as compared to New Zealand data. And the purpose of this is to identify which of the ground motion models are actually suitable for this New Zealand National Seismic Hazard Model. And although this wasn't the sole determinant of how we informed the logic tree weights, sometimes the things we looked at did kind of play a part in each person's kind of individual opinion about our degree of belief in particular models. So again here, just kind of three scatter plots and a few histograms showing the data sets that I used for each of the three kind of tectonic types: crustal earthquakes, interface earthquakes, and slab earthquakes. Here I've kind of shown in the red dots the data that I did use in the evaluation, and in the gray, the ones that were discarded for various reasons that I won't get into, but associated with essentially aligning the ground motion, the database with the valid range of ground motion models, and also discarding low quality data. So crustal earthquakes on the left, most of our data is for the crustal earthquakes, and then less so for the interface earthquakes and also slab earthquakes. In terms of how the data set looks on a map, this is how they look, again, on the left for crustal, where we have most of the earthquakes that we've considered, kind of within the middle of the South Island or the north of the South Island, but scattered elsewhere across the country as well. For interface earthquakes in the middle, where we have our two subduction zones, the Hikurangi subduction zone on the east coast of the North Island, and then also the Poisega subduction zone at the bottom of the South Island, and in the kind of shallow ranges of those two subduction zones. And then on the right-hand side, we have our slab earthquakes, where we have them again at the two subduction zones, but over a wider range of depth. So the ground motion models that we considered, we did have a kind of preliminary trimming to get a short list of them. We looked at 8 crustal models in the end, 10 interface models, and then 10 slab models. And the ones that are highlighted in blue, not expecting you to read them all, but the ones that are highlighted in blue are those that are New Zealand specific or New Zealand regionalizations. And as I mentioned a few slides ago, none of these were developed solely from New Zealand data, but started with some kind of global model and then made adjustments to be more New Zealand specific. On top of that, we have a few very well-used models. So the NGA West 2 models are pretty much uniformly understood or agreed upon to be kind of the most robust models or global models for crustal earthquakes. We also have kind of recently developed NGA subduction models over here. And then a few of these other ones are foreign models that are kind of region specific, but they are ones that have been kind of used commonly in seismic hazard analyses. So we included those as a part of our evaluation as well. The only plots I'm going to really show from our evaluation is this style, where I have the model prediction bias on the left-hand side, and then vibration period for spectral acceleration on the x-axis. And basically, each line is a particular ground motion model. And then if the line plots above the x-axis, then it's actually indicating that there's under prediction overall for that model. If it plots below, then it's over predicting across the model, across the data set for that model. So we can see that actually for crustal earthquakes, all the models are actually not too different from one another, indicating that maybe for crustal earthquakes, we actually have the least epistemic uncertainty. On the right-hand side in this plot, similar thing, except now the y-axis is total standard deviation. So we kind of had to assess what the standard deviation was when compared to New Zealand data as well. This plot is then for subduction earthquakes. Sorry, the last one was for crustal. This one's for subduction earthquake ground motion models. And we see actually the spread between models is larger now. It's indicating there may be a bit more epistemic uncertainty associated with this, and our modeling is not as precise. And then also the total standard deviations. And then lastly, slab earthquakes, which actually have the largest spread in model prediction bias, and also some relatively large total standard deviations, as I'm showing here on the right. This was kind of the highest level summary that I could provide in terms of the model performance, but of course we looked at other things in our evaluation. So for example, we did look at things like parameter dependence of residuals. Was there any trend with magnitude, site condition, distance, those kind of things to ensure if the models were actually scaling in the same way for New Zealand conditions as they were for overseas conditions. We also looked at comparison against specific subsets of data, because there were particular things that we were trying to target in our understanding. And also comparison between models for hazard dominant scenarios that are not represented in the ground motion database. I mentioned earlier that we are very limited on the amount of large magnitude earthquakes that we have observed within our kind of instrumental history. So the scenarios that typically dominate the hazard are these large magnitude earthquakes, but if we can't understand how the ground motion models are performing at these large magnitudes, then we need to do something else. And the best thing we could do was get together as experts and try and understand how each of the models looked for these hazard dominant scenarios. The last thing I note here is we also looked at a comparison of published model standard deviations, something that is not often presented, and I'm not presenting it today either, but important for probabilistic seismic hazard analysis. We made some decisions on what ground motion models were suitable and weren't suitable. So in terms of ones that we kind of decided to exclude based on these analyses, Basically, the McVeary et al. 2006 model, which is the one that was used in the previous version of the National Seismic Hazard Model, we decided to exclude that, as well as the Zhao et al. 2006 model. The reasons I cite is arguably they are outdated. McVeary model in particular only uses data prior to 1996. So that's a very limited amount of data. And also chances are that data is very low quality. So we've omitted the McVeary and Zhao models. We've also excluded Abrahamson et al. 2016 and 2018. The main idea here is that we considered that they had actually been superseded by more recent developments, like the Abrahamson and Gilles 2022 NGA submodel. The last note I make is that we also decided against using the New Zealand regionalizations of the NGA subduction models. The main idea here was that they were calibrated to the more limited Van Hout 2017 strong motion database, which has not that much data, but also the metadata quality is highly uncertain and questionable. And also in our evaluations, we didn't find that they performed any better than their global counterparts. So we opted to just use the more stable and more robust global models. I only bring up two particular first order adjustments that we made based on our evaluations. The first one is that we did apply some reduction in standard deviations for the Parker 2022 model and the Kuhn 20 model from NGA sub. That was because we found that their standard deviation models didn't seem to account for the reduction in standard deviation that comes with intense shaking and nonlinear site response. So we kind of added that in a post hoc manner. I've heard Brendan give the explanation for this one at least 5 times. So if anyone is interested, I'm sure he can pull that one out of his hat in the Q&A session. Second first order adjustment, which I will talk about, is this back arc attenuation adjustment, because this was kind of something we found directly out of the evaluation. So basically the idea here is that if we plotted out the systematic site residual, so the misfit for particular sites between observation and prediction, we noticed that there was a very significant cluster of sites in the kind of northwest part of the North Island where we were getting some pretty significant overprediction. So blue is a negative residual, which means overprediction. And our belief is that this is because these ground motion models, or a lot of them, don't actually account for this thing that we call back arc attenuation. The main idea here is that if we have some kind of subducting slab, like we do in the Hikurangi subduction zone, we have the Pacific plate going beneath the North Island, then an earthquake that happens in the slab going towards the west and north side of the North Island has to travel through this kind of high attenuation material that's like partially melted crust and mantle that actually reduces the amplitudes more than other kind of parts of the earth. So we found this out quite later in the timeline, so we couldn't actually adopt anything rigorous to kind of adjust for this. Brendan went through scraping the literature and decided that perhaps it's best if we just use an existing kind of factor from one of the models that we considered. So from the Abrahamson et al. 2016 model, they do actually account for it with this intraslab back arc factor that is based on how much of the path of the waves travel through the Taupo volcanic zone or volcanic back arc. It has some amount of sorry, it's not based on that. If it does travel through the back arc, then it does lead to some reduction for particular intensity measures. So if we applied that to the ground motion models and ran the predictions again, then this in the middle is what we get. And yes, they're still blue, but not as dark blue. So we do believe that this is an improvement, and other evidence that we did look at did also kind of correlate with that it is an improvement. So I'm going to now present the logic tree that we came out to. So very briefly, because there's not whole lot to say about it, but we had a logic tree that was determined through expert elicitation for the 3 different tectonic types. Active shallow crustal is the one I'm showing here right now. The Atkinson New Zealand specific model has its own branch. Stafford as well has its own branch. And then all the other ones that were kind of the existing models have a branch collectively, and they're all kind of uniformly weighted within that branch. But actually, when it came to the expert elicitation, there was some kind of favoring of the Stafford model, which received a higher weight between the 3 kind of branches at this level. For the subduction interface, there was no subduction model for the Stafford 2022 models, but Gail Atkinson did develop one. So there's the Atkinson model in one branch, and then each of the NGA submodels with a separate branch as well. And what we see is that basically the weights that were decided were not too different from just being uniform. And then likewise for the subduction slab, it follows the same kind of structure as the subduction interface. And then the weightings, just like subduction interface, not too far off from just being uniform between the four. So these are the logic trees that were used in terms of the probabilistic seismic hazard analysis calculations that fed into the National Seismic Hazard Model. So then the last thing I want to talk about is examination of hazard sensitivities. So the first thing I need to mention on the slide is that Sanjay was the one that led and basically did all of this work himself and was kind enough to put me as a co-author. So full credits to Sanjay for actually doing all this work. But basically, what did we do here? We compared calculated seismic hazard using different combinations of old and new models. The purpose is to understand how each model update influenced the calculated hazard. So when I talk about old and new models, basically the old model is the previous National Seismic Hazard Model from 2010, NSHM 2010. And then within that, of course, there's the seismicity rate model component, and then the ground motion characterization model component. And then in terms of the new model, NSHM 2022, also it has an SRM and a GMCM. So these kind of acronyms are going to come up just a little bit in the next few slides. We're going to look at hazard curves for 4 particular locations: Auckland, Wellington, Christchurch, and Te Anau. So firstly, we're going to look at the influence of the GMCM update. Each of these are hazard curves for the 4 locations: Auckland, Wellington, Christchurch, and Te Anau. Basically, what this hazard curve is showing is on the y-axis annual probability of exceedance. So a larger value is essentially a more frequent occurring event. And then down the bottom is a more rare event. The x-axis is I've chosen to be peak run acceleration as my intensity measure. But basically what each hazard curve is showing is that as we look to more and more rare events for probability of exceedance, we expect that the intensity measure being exceeded is a larger value. So the green lines here are the previous National Seismic Hazard Model, NSHM 2010. And then the blue dashed line is using the seismicity rate model from 2010, but updating the ground motion characterization model for the 2022 version. And we see that if we draw a horizontal line across anywhere, basically we're looking at values corresponding to the same kind of annual probability of exceedance or some probability of exceedance in a particular time period. So this black line is indicating 10% probability of exceedance in 50 years. And then the values that it's intersecting with each of these lines is telling us what the value is for each of those calculated hazards. So a larger value means a higher value of hazard. So we see that across the board, all 4 locations, we are seeing an increase in the dashed blue lines compared to the green lines, which means that the new GMCM is actually increasing the calculated hazard everywhere. If we look at hazard map ratios across the country, basically this is a calculated hazard with the updated GMCM, but the old SRM divided by the old NSHM. So blue divided by green in terms of these hazard curves. What this is essentially doing is isolating the change from updating the GMCM. And we see that across the board for both 10% probability of exceedance in 50 years and also 2% probability of exceedance in 50 years, we have increased all across the country. So we can pick this apart just a bit more. So I have 2 more kind of ways that we do this. Firstly is if we just update the crustal ground motion models. So we keep the subduction interface and slab models the same. That's what these red lines are now showing. And we see that for Auckland and Christchurch, actually the update of crustal ground motion models is the largest component of the increase in calculated hazard because the red dashed line is close to matching the blue line now. For Wellington and Te Anau though, it does have a significant increase, but there is something else also contributing. And we'll see that on the next slide. In terms of hazard map ratios, I now have plotted essentially the red hazard curves divided by the green ones. So that's the old SRM with only the update to the stable crustal earthquakes divided by the old NSHM. And this is essentially isolating what the increase is based on updating the crustal ground motion models. And we see that it has a kind of widespread increase all across the country as well for both 10% in 50 years and 2% in 50 years. So red being increased, blue being decreased. Last one is I'm going to show is the influence of interface ground motion models. So now the red line is actually the SRM 2010, so the old seismicity rate model, and only an update for the subduction interface models. And we see actually for Auckland and Christchurch, the red line is essentially overlying the green line, which means that there's not much change there. That makes sense because they're quite far from subduction zones. But for Wellington and Te Anau, we do see some significant increase in the seismic hazard at very rare events or very low probabilities of exceedance. And of course, that makes sense if we then look at these hazard map ratios again, now isolating the change from just the adoption of the new subduction interface models, we see around the subduction zones, Pickering subduction zone here, and also Poisega subduction zone, we have moderate or modest increase for the 10% in 50 years, but actually more severe increases for those rare events, rare or low probabilities of occurrence. So I'm short on time, but this is what's just going to be my overview of the GMCM. We've talked about that already. So the last thing I want to talk about is future work. So basically, there's a lot more to be done, of course. The first point I note, which I won't talk about too much, is that more detailed regionalization and these non-ergodic empirical ground motion models are kind of an obvious next step for us. All that really means is developing these empirical ground motion models that are more New Zealand specific and actually take in New Zealand specific inputs rather than kind of global values. And by doing that, hopefully we can actually obtain more accurate and precise ground motion predictions, which would lead to more accurate seismic hazard. We're also looking at how we do site response modeling in the Wellington Basin. So work being led by Chris de la Torre is looking at if there are systematic region-specific residuals that exist within the Wellington region based on whereabouts you are. And then we're also looking at physics-based ground motion simulation of basin response across the basin as well. The last slide I have is talking about another project that we're kind of looking to commence. It's titled Creating a Physics-Based Understanding of the Spatial Correlation of Earthquake-Induced Ground Motions in Regions of Complex Geology. So this is a project that is important because, but often neglected. So spatial correlations of ground motion is very important because where the ground motion is perhaps exceptionally strong, you can imagine that regions nearby would also be exceptionally strong. So what we're going to try and do as part of 3 different objectives is to kind of synthesize observational data with empirical analysis to understand what kind of intrinsic correlations exist within the data itself, and then analyze similarly physics-based ground motion simulations from our CyberShake platform to understand what kind of spatial correlation structures exist within simulations. And then what we often find is that the residuals between observation and simulation also show some kind of spatial clustering. So by actually doing analysis residuals between observation and simulations may actually lead us to new insights and phenomena that will give us improved modeling. So it's funded by a Marsden Fast Start at the moment, and I have to advertise every time I talk about this that I am seeking an interested PhD candidate. So if you are interested, feel free to flick me an email. So with that, thank you for your attention.